Okay, so lesson 37, differentiation by use substitution or chain rule. Either way, it's derivative still, okay? So talking about the idea of use substitution, and even if you don't walk away from here today really using use substitution, there are times in calculus when we'll use use substitution for things, whether it be chain rule or something else. So the idea is being able to figure out, okay, what can we let u represent that then gives us a simpler expression to take the derivative. So like right here, as we look at y equals e to the x squared plus 2. That's not quite so simple to take the derivative of, because we have e to some power that has a derivative, but then the part we're adding in today is that power itself has a derivative. And so it's how do we incorporate this all together. In this case, when we talk about use substitution, the idea is the more complicated part is that x squared plus 2. So if we just talk about this as e to the u, we know the derivative of e to the u, don't we? And then we can also talk about, okay, what is u? So u was in place of x squared plus 2. And we'll talk about, okay, what's the derivative of x squared plus 2? Again, once we get into this, I don't know that you'll really separate them out, but it's having that ability. The idea here, if we have this difficult thing, right? Well, not difficult, but these three terms have a derivative, right? But we also have to take the derivative of something raised to 100. That's our power rule there. So we've got this inside, which could be our u, and so the more simpler version of this is u to the 100. Again, being able to take the derivative of u to the 100, and then being able to take the derivative of what you replaced. Okay? This one, natural log of something. So we know the derivative of natural log of u, right? And we can find the derivative of that something inside. We often see this with sine, with our trig functions. So sine of something, so we could think sine of u. We can find derivative of sine of u. We can find derivative of x squared minus 15. And then this is a different one, sine x raised to the third. So the overall thing there is, okay, what is the derivative of something raised to the third? But then we're also going to have to talk about, okay, what's the derivative of sine x? So kind of two things going on at once here. So the derivatives of many functions can be found doing use substitution, okay? And so the idea here, y equals e to the x squared. If we talk about this one up there, e to the x squared, what is the derivative of e to some power? Well, the derivative of e to the x is e to the x, right? So the derivative of e to some power is e to that power. But then what we have to say is, okay, so derivative of e to some power is e to that power. But then what's the derivative of that power? And this is where chain rule works, because now you have to say, okay, the derivative, what is the derivative of x squared plus 2? And that's 2x. So you're taking the derivative of the main item, but then also the derivative of whatever is inside of it. So the derivative of e to some power is e to the x squared plus 2 times the derivative of that power, 2x. This right here is just rewriting it. We don't generally say e to the x squared plus 2 times 2x. We generally bring something like 2x out front of it and have 2x e to the x squared plus 2. This right here is putting it in symbols. Okay, so being able to understand the f and g stuff. So given f of g of x, so where f is your outside function, like in this case, f is the e to the u, and g is the what's inserted it, the x squared plus 2. So official notation, which is good to see notation, that's definitely something we have to understand in AP, is that in order to do the derivative of f of g of x, we do f prime of g of x, so we're doing the derivative of f, so the derivative of the outside function, leaving g of x as is, so leaving the inside, and then timesing by the derivative of the inside. So when we talk chain rule, we usually say derivative of the outside, leave the inside as is, times the derivative of the inside. So in words, derivative of the outside, leave the inside the same, times the derivative of the inside. And this right here, that right there is your chain rule concept. And that's what you'll hear me talk about a lot today. As we go through, I kind of incorporate the use substitution idea though, in that I try and make you think, okay, what's the outside function and what's the inside function where I can put u in place of. Ready to try some examples?
I think it'll make much more sense.
Probably. Yeah, I know. I need to kind of explain the background of all of it, but yet it's probably a dropping mess in your brains right now. Is that what you're saying?
I mean, it's not. I'm not grasping it. Like I get what you're saying. I just think I have to apply it.
Apply it to really make some sense of it. Okay. So let's look at example 1. If f of x equals x squared plus 2x raised to the power of 10, what is f prime of x? Now, at least on the first one, and I don't know, I think in my notes I have it done all the way through. But I want you kind of thinking, okay, what is the inside here? As we look at, this is overall what's our evolved function, and so then what's the inside? And I don't know if I'm making sense when I ask that.
Inside is x squared plus 2x.
Okay, so if we say the inside, that x squared plus 2x, if we replace that with u, what is the overall function that we're trying to take the derivative of here? Can we take the derivative of u to the 10th? That's a pretty basic concept, isn't it? And in fact, y prime, what is the derivative of u to the 10th? 10u to the 9th, right? Okay, so now let's go into our actual problem here. We have f of x. We're being asked to find f prime of x. So right now, this is something. That's something which is at x squared plus 2x, right? So that's something raised to the 10th. How do we do the derivative of something raised to the 10th? Okay, so we multiply it by 10. This something stays the same. So we're going to keep x squared plus 2x and then raise to the power of 9. That's what we did with u out to the side, isn't it? So the overall power being something to the 10th. Do that, but then don't stop there, because then we don't just have u in there. What do we have? X squared plus 2x? What's the derivative of x squared plus 2x?
2x plus 2.
Derivative of x squared is 2x, plus the derivative of 2x is 2. That is a version of your answer.
I assume you want to simplify.
Well, it's a matter of how much can you simplify it, though. There's only so much simplifying that can be done here. In all honesty, this answer isn't half bad in my opinion. Okay? I say there's a little bit of simplifying that if you look at this type of answer in the book, and this comes down to, a free response problem, perfect, great, stop here, you don't need to go any farther. Multiple choice, what form did they give you? And so, one thing the book points out, what do you notice about 2x plus 2? Okay. 2x plus 2 has a GCF of 2. Agree? So, the option of what I have written down from the book is they factor the 2 out. That 2 is a constant, yes? So where can I take that 2?
Put it with the 10.
I can put it with the 10. So I can say f prime of x, so 10 times 2, which is 20. still have the x squared plus 2x raised to the ninth. And then times, instead of 2x plus 2, since we factored the 2 out, it's x plus 1. That's the answer I have circled in my notes. Okay, as I said, I'm perfectly fine with that top answer. I don't see anything wrong with that top answer. But it's, understanding what they want you to understand there. Questions on example 1? Okay, shall we try example 2? If h of x is the cube root of x squared plus 2x, what is h prime of x?
Make it an exponent.
Can we what?
Make an exponent.
We're going to have to make an exponent.
Sure.
Yeah. Okay, we're going to have to make an exponent in order to be able to even talk about this problem. So it's going to be h of x equals x squared plus 2x raised to the 1/3. Now, if we talk about it, if we take those insides out, what is the big thing we're taking the derivative of? Yeah, it's something raised to the 1/3, right? So if you think about this being u to the 1/3, okay, make your brains work. What is the derivative of u to the 1/3? 1/3 out front, u to the 1/3 minus 1 is negative 2/3. No one said this one was going to be pretty, right? So now, if we do our derivative here, x squared plus 2x raised to the 1/3. We just said the overall function is something raised to the 1/3. So the derivative of something raised to the 1/3, 1/3 times the something raised to the negative 2/3. My something, I like to use that word in there, just, is x squared plus 2x. I left my insides the same. Am I done, though? No, we did derivative of the outside, leaving the inside the same, and now we're going to say times derivative of the inside. What's derivative of x squared plus 2x? 2x plus 2. Sounds a little familiar there, doesn't it?
It does.
Okay. If you want, like the last one, there's a GCF of 2 there, isn't there? Okay. So with there being a GCF of 2, you could take that 2 out front and multiply it by the 1/3, right? So I have 2 different ways I'm going to write it out here. One way is kind of like what we did last time. So 2 times 1/3 becomes 2/3 times x squared plus 2x raised to the negative 2/3 times 2x plus 2 is no longer 2x plus 2. It's x plus 1. That's one option I have written out in my notes. The other option involves the fact that we left a negative exponent. And we can leave a negative exponent, or we can make it a fraction. So a variation on this one, negative exponents go to the denominator, right? So x squared plus 2x raised to the 2/3 can go to the denominator. x plus 1 is going to stay in the numerator. What about that 2/3?
It's out for the whole thing, right?
Well, out in front of the whole thing, but what I can do is I can put the 2 in the numerator, the 3 in the denominator. A third option, if we really wanted to, we could go back to radical form. I'm not writing that out, but you could leave it in this fraction form and we could go back to radical form. Starting to see the concept a little bit? And really what we're doing in the notes here is we're just trying a bunch of different things. You know, the first one, we just had a power to the 10th. Now we threw a radical in. The next one, we're going to throw in natural logs. So, you know, just remembering all the, you know, kind of putting all of our derivatives together. So, example 3. If g of x is natural log of x squared minus 42, what is g prime of x? So what's my big function here? Yeah, it's the natural log of that stuff inside of it, right? So if it helps you to think like this, and again, I'm just trying to get you to identify, okay, what's the big function I'm trying to take the derivative of? So what's the derivative of natural log of something? 1 over that something. So derivative of natural log of u is 1 over u. Now, except ours is not u. Yeah, so the derivative of natural log of x squared minus 42. Okay, its derivative of natural log is 1 over the inside. So 1 over x squared minus 42 times the derivative of x squared minus 42, and the derivative of x squared minus 42 is 2x. I don't teach it like this, but what it comes down to, guys, we haven't talked about, but we could have used the chain rule on every single problem we've done this year. But I haven't talked about that because we're used to our insides being x. And what's the derivative of x? 1. So have we really needed to write a times 1? We don't. And I don't know if there's teachers out there that introduce the chain rule always, but I wait until now to introduce it. So, okay, my guess is I made this as one fraction. Yep. So g prime of x, if we put it back as one fraction, 2x over x squared minus 42. Speaking of multiple choice, you would see this put together as one fraction, which is why you need to be able to identify, okay, it's 1 over, but then I usually put that other piece back in my numerator. Example 4. F of t equals sine of t cubed minus 15. Find f prime of t. So are you asking yourself, what's my outside function? Sine, right? So if we think about a sine of u, what is the derivative of sine of something? Cosine of something. So derivative of sine of u is cosine of u. Except, of course, it's not u. You know, we're learning chain rule. Nothing's going to be basic today. So, f prime of t. The derivative of sine of that inside is cosine of the inside. Am I done? No, that'll be the common mistake you guys will make in the, upcoming days. Or maybe not today because it's fresh in your mind, but after a day or two, that'll be the mistake we'll make is we'll just stop here. times derivative of t cubed minus 15, which is 3t to the second. My guess is, okay, leaving it like that would be acceptable. I tend to put the 3t squared out front because we tend to have other pieces being out front of the cosine. So there's not really cleanup we can do here. So 3t squared cosine of t cubed minus 15. Making good progress here. You guys are going to stop me if you have questions, right? Okay. Example 5. Y equals sine cubed x. What is dy dx? What is the outside power here? Or the outside function, I guess, is how I need to ask it.
So since sine is being cubed, would the outside function be x cubed?
So, well, or something to the third. Like when okay, so first of all, realize sine cubed x, I don't know if it's necessary or not, but that's the same thing as saying sine x raised to the power of 3, right? So it's that function, sine x raised to the power of 3. So when we think about, if we're thinking u substitution here, our overall power is, this is u to the third. That's our main thing we're going to take the derivative of. Then we'll do the inside. So the derivative of something raised to the third, about 3 to the second. Now I know why you made that mistake in your test. I think that cost you a point on the test, if I'm not mistaken.
It might have.
Because there's a spot where you wrote a wrong number, and now I'm seeing why you did it, because this is exactly the mistake you made. So, unless I'm remembering wrong, but okay. They want dy dx. I started to write y prime. Derivative of sine x raised to the third. So derivative of something raised to the third is going to be three times something raised to the second times cosine. Cosine x, that is. Okay? So derivative of something to the third is 3 something to the second times the derivative of something, which is cosine x. I don't know. I don't think you'd see it like this in in a multiple choice type format. I think you would see 3 sine squared x cosine x is the form I would think you would take on. I don't think you see it written with the parentheses. I just kind of did that as a teaching thing. Okay. And the other thing I guess you could do is you could write 3 cosine x sine squared x, but interchangeable there. Okay, last 3. Y equals cosine of e to the x, find dy dx. What's our outside there? What's our big function? Cosine. Okay. So if y is cosine of u, what's the derivative of cosine of u?
Negative sine of u.
Yep. Negative sine u. So if y equals cosine of e to the x, dy dx, derivative of cosine of e to the x, derivative of cosine of that is negative sine of that times the derivative of that. Derivative of e to the x is e to the x. Again, I would probably say put the e to the x out front. So dy dx is negative e to the x sine of e to the x. Okay, example 7. Y equals e to the x plus 1 raised to 1/2. What?
So is it just u?
Right. The overall function is something to the 1/2. So what's the derivative of something to the 1/2? 1/2 of that to the negative 1/2. So they actually asked for y prime here. We're doing the derivative of e to the x plus 1 raised to the 1/2. Derivative of the outside, so 1/2. Still e to the x plus 1 raised to the negative 1/2. Times derivative of the inside, so derivative of e to the x plus 1 is e to the x. Options include pulling that e to the x out front, so 1/2 e to the x times e to the x plus 1 raised to the negative 1/2. That's one option I have written in for answer options. Or
We do half e to the x over e to the x plus 1.
almost. Okay, so yes, take the negative down to the bottom, right? So if we take that negative to the bottom, so we're going to make this fraction, right? E to the x plus 1 becomes a power of positive 1/2 when I move it in the denominator. E to the x is going to stay on top. We don't want a fraction within a fraction, though. So the 1/2, think about the 1 being in the numerator and the 2 being in the denominator. So e to the x over 2 e to the x plus 1 raised to 1/2. Okay. One last one. Y equals natural log of absolute value of cosine x. Find dy dx. What's the outside? L and U. I'm just not using x because x is part of the problem. That's the key. So I get it when you say L and x. So what's the derivative of natural log of something? 1 over the something. And I guess they had absolute value in this one, didn't they? So let's see, we're calling this dy dx here, aren't we? Derivative of natural log of something is going to be 1 over something. So 1 over cosine x times.
So would you keep the absolute value of that? It's either times negative sine x or times sine x.
We don't worry about the absolute value. The absolute value is just saying that, okay, cosine of x has to be positive for this to work because the inside of a log has to be positive. But when we do the derivative, we don't really worry about the absolute value.
So it's just negative sine.
Right. So natural log becomes 1 over the insides times the derivative of the inside, so times negative sine x.
So it's negative.
Oh. So I was just going to make it a fraction to start with. The fact that it's, if you leave it as this, you miss what it could become. If we put it back as a fraction, then it's the negative of sine x over cosine x. But then once you see it as a fraction, that should click, oh, sine over cosine is always tangent. And so we can say here that dy dx is negative tangent x. That's one of the special derivatives we eventually see in a list later on down the road. Yes?
With the negative sine x over cosine x, would that be input or
If you leave it like this,
yeah?
it's equivalent. Multiple choice, you're going to see it like this. Free response. I mean, free response, here's the deal. This isn't going to be the final answer to a free response problem. You're going to be doing other stuff. And so it would probably be important to be able to convert it to that, you know.
Yeah.
So I don't know. I mean, if you're asking, am I going to count that wrong on something? I don't know. Because it is equivalent. If it's equivalent, I don't usually count it wrong. Right? So, I mean, although those equivalent things are more about when it's in terms of a number. Here, since we still have x's, I don't know. I would go this if you can. Okay? Questions?
How about the tangents? Because now I'm intrigued.